That's, all right. Okay, let's get started. Just so everybody's aware, I only have one real announcement, and that's about the homework that's due on Wednesday. Right now, I have it due on Wednesday, but this homework, there's a chance I may push back because I missed some class with being sick and whatnot. For those of you in steel design, that homework probably won't get pushed back because we're going to be fine to meet all of the the topics in class. Like, you'll be well equipped to handle that homework, especially after today. But this one, the big sticking point really is MN, and I'm not sure we're going to get to MN today, so we'll see. But we're definitely going to do transform sections and cracked moments of inertia today. So with that, I'm just going to sort of get right into it. So just so everybody is aware, let me go back a couple slides just to make sure everybody's on the same page. Really what we've been talking about over the past couple days is this, the cracking moment, okay? So basically we assume that the beam is, let's go back a little bit further. So what we're doing right now is we're sort of trying to investigate the behavior of a typical reinforced concrete beam. And so we've broken that up into stages. The first stage is the behavior of the beam in its uncracked state. So what I mean by that is we're just taking, this is under very low levels of stress, and we're taking load and we're applying to it, and we're assuming that the beam behaves basically the same as it did in Engineering 216, just regular old everyday bending theory. And this will hold true until we reach the cracking moment. And the cracking moment is really just when the tensile stress in the extreme fiber hits FR, hits the modulus of rupture. And so we did a couple problems investigating that, and really up until now we have not considered the presence of the rebar because it hasn't become relevant. The beam hasn't cracked yet. So we're just assuming that the beam is one single cohesive unit, and we just determine what's the moment that causes it to crack. And the last couple examples that we've been doing have all sort of been revolved around that idea. All the moments up until the cracking moment. Well, what happens past that? What happens if the beam cracks? So if the beam cracks, does that mean that the beam disintegrates into a Michael Bay explosion and that's it? No. I mean, the beam can withstand load well beyond its cracking moment. So we start to enter stage 2. So how does the behavior of the beam change once it's cracked? Well, basically, when we're looking at a cracked cross-section, we're assuming that all of the concrete that is in tension is ineffective, because once it's cracked, those fibers have separated. I mean, you can't really apply load to something that's split in half, right? So everything that's in tension, we assume, every concrete element that we assume, that's in tension, we assume is ineffective. So really we only have two elements resisting load. We have the concrete remaining that's in compression, and then we have the rebar. So now the rebar is going to come into play. Now the problem is we now have a beam that is comprised of two materials. So in Engineering 216, you might have remembered the math regarding a composite beam. A beam made of one or two materials. Well, we have a beam made of two materials here because we have concrete in compression, we have steel in tension. See, the problem with that is sigma equals my over I and all these nice, pretty equations from mechanics and materials that we've been using, they all assume that the beam is made of one material. And so if the beam is made of two materials, they don't directly apply. Hence, or enter the use of a transformed section. So the idea behind a transformed section analysis is what we do is we take this beam that's made out of two materials and we transform it into a beam that's made of one material. Okay? So what we will end up doing for our analysis is our transformed section is going to look something like you see here in the middle. So we're going to have a neutral axis. We're going to have to figure out where that neutral axis is. That's going to become a discussion here in a second. And so above that neutral axis, if it's in positive bending, all we're going to see is concrete in compression. Below that, we're not going to see any concrete at all in tension, but we are going to see some rebar. Well, what we're going to do is we're going to take that rebar and we're going to transform it into an equivalent lump of concrete. And we do that by multiplying the area of the rebar times that modular ratio n that I mentioned earlier. So remember, the modular ratio is the ratio of the E value for steel divided by the E value for concrete. So we're going to take the ratio of those two, and that's how we're going to transform that steel into an equivalent lump of concrete. And then we're going to compute the moment of inertia of that transformed section, and that's going to be the moment of inertia of the cracked section. So just to give you kind of an idea of where this is headed. So, yes?
Whenever being cracked, is the rebar more of like a temporary fix, or is it that when you need to repair the beam, or do they just kind of leave it because the rebar is, I think it's like
Well, that's a good question. So let me say a couple things about that. So first off, I think a better way of looking at it is looking at it like this. Okay, so take a look at this image. I have a beam that's simply supported, subjected to, let's say, a uniformly distributed load. Let's say its own self-weight. Would you agree that the bending moment diagram looks something about like this? Okay, so a better way, I think, of answering that question is not that, like, you're looking at it as a singular event. The beam cracks or it doesn't. What I'm saying is that there's always going to be some regions of the beam that are cracked and some that aren't. Okay? So what I'm saying is that for these regions where the beam is experiencing cracking, this is where the rebar takes over. Okay? But there's always going to be regions that are cracked and regions that aren't. Okay? The idea of a beam cracking, look, there are only, for those of you that had civil engineering materials, and I'm sure you learned about all these different types of concretes, you know, type 1, type 2, type K, all this, there are only two types of concrete in this world, and that's wet and cracked. So that's a joke, but not really. I mean, concrete cracks, and there's really nothing you can get around it. So concrete cracking is something you're always going to deal with. So really, it's more about making sure that you're handling it appropriately. So to a little bit of a taste of things to come, when we start looking at deflections, okay, deflections, you need a moment of inertia, right? Y'all remember that from structural analysis. Well, what moment of inertia do you use? Do you use the gross moment of inertia, or do you use the crack moment of inertia? The answer is neither. You use sort of a weighted average between the two, depending upon how much moment you have on the section. So it's always a little bit of both. That was a little bit of a convoluted answer, but did I kind of address what you're talking about? All right. Any other questions? Okay. Did you like that, wet and cracked? So that's an old joke. So okay. So what I want to do is I want to look at computing a cracked moment of inertia, and particularly looking at computing bending stresses in this beam. Now, we have a beam that is subjected to 70 foot kips. Maybe the first question we'll answer is has this beam cracked? I mean, the question says calculate the bending stresses. Well, the beam is subjected to 70 foot kips. What if the cracking moment is 120 foot kips? Maybe all you got to do is just sigma equals my over I and go home. You know, that's it. Well, let's see what happens. Let's see what the bending stresses look like. So now, a couple things about notation. Like I said, it's B wide, it's H tall. That term D, the distance from the top to the tensile steel. So later on, I'll start introducing some notation to describe compression steel, if you ever have steel up top. And you'll always see me throw some primes out. So like D prime would be to the top to if there was steel, let's say, up here. The area of the steel up here would be AS prime, so just so you're aware. Like I said, I'm easing you into this, this notation a bit. Now, just so you're aware, on the rebar, I have 3 bars. The bars are number 9 in size. The area of a number 9 is 1 square inch, so the area of steel is 3 square inches. Everybody okay with that? So if it was 3 number 8s or 3 number 7s, you would need to look that up. Remember, I have posted on Blackboard a chart that shows if you have 7 number 11s, what's the area? If you have 3 number 6s, what's the area? So make sure that you have that available to you. Okay, so let's do some basic calcs. So let's see what we can come up with. Now, this beam is subjected to a bending moment of 70 foot kips. So let's do some calcs right off the bat. So first off, let's look at the cracking moment. Bless you. Now remember, we compute the cracking moment by taking FR IG over YT. Okay? Now what is IG? And how do we compute that for a rectangular beam? Well, no, this is just a rectangle. BH cubed over 12. We don't have to break out the I plus AD squared because we don't have a T-beam or anything weird like that. It's just a regular old rectangle. So that's 20 cubes. That's 4,000 inches to the fourth, right? No, 8,000. 8,000. All right. What's YT? I want to make sure everybody's paying attention. What is YT? Like, what does it mean? Why are you getting 10 inches? Centroid. So exactly. So from the centroid to the very, 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 very bottom, to the extreme tensile fiber. So how far is it from the centroid to the very, very bottom? It's 10 inches. Remember, if it was a T-shape or some weird cross-section, we'd have to determine where the centroid is. But we don't have to worry about that with this problem because it's a really simple cross-section. Now, what else do we need? We need FR, right? Now, how do we compute FR? What's our formula? There we go, 7.5. There we go. Now, let's go back. Here's the problem. We have a concrete strength of 3,000 psi. Now, the problem doesn't say whether or not it's normal weight, but I'm going to, for the sake of discussion, assume that this is normal weight. So if we have normal weight concrete, what's that mean? Lambda's 1. And then what do I do here? Square root of what? 3,000. Remember, you put in PSI, you get out PSI. And so what does that come out to be? 410.8 PSI. Do I have a second on that? So therefore, our cracking moment, so we have 410.8 PSI. We have 8,000 inches to the fourth. We have 10 inches. What does that come out to be? Now, what are the units? It's a moment. Inch pounds. So it's going to be a big number. 328,000. Inch pounds. And can you go ahead and convert that to foot kips? How do we convert that to foot kips? What do we do? No. Not by 144. We're not doing inches squared and foot squared. We're dividing it by 12 and then dividing it by 1,000. So what can we quickly divide it by? 12,000. So if we divide that by 12,000, what do we get? 27.4 foot kips. Okay, is everybody okay with that? Okay, now, how much moment are we actually putting on this section? 70. So what does that mean? Oh, it's cracked. It's well beyond cracked, right? Okay. So we'll say M applied is 70 foot kips. And we'll say, therefore, beam has cracked. I think that's a fair statement, right? Okay. Any questions? All right. Now, before we start going into transform sections, we need to look at a modular ratio. We need a value for N. Now, typically, N is E for the steel divided by E for the concrete. Now, the reason why is because we typically take N as the bigger E value divided by the smaller E value. We always want N to be bigger than 1. Okay? Now, N for the steel, or E for the steel is what?
29,000.
There we go, 29,000 what? KSI. I want that number burned into the back of your memory. Now, how do we compute E for the concrete? What is that? What do we do? She's right. There is a formula. What is it? There you go. Exactly right. 57,000 times the square root of FC prime. And that is the case for normal weight concrete. If it's not normal weight, there's a little bit more of an involved formula where you actually use the unit weight. But for our purposes, this is perfectly fine. So this is 57,000 times the square root of what? 3,000 what? PSI. So when I compute this, what's the answer going to be? And what is this in? So you're going to have a unit conversion issue you got to deal with. So 57,000 times the square root of 3,000 is going to give us what? 3 million?
222,000.
Yep.
18.58.
Okay, and so that's 3122.02 KSI. Fair statement? So, therefore, N is 29,000 divided by 3122, which is what? Remember, N is always unitless, so you should be taking a PSI over a PSI or a KSI over a KSI. Say it again? 9.3. Do I have a second on that? All right. All right. Typically, when we compute N values and when we utilize N values, we always use the nearest whole number. So for our purposes for this problem, I'm going to take N to be 9. Okay? So we're going to take N to be 9. Okay. Everybody with me? Yeah, I would. Usually, though, just through serendipity, that doesn't really happen. It's usually pretty easy to figure out. Although, if you have like a really odd FC prime, that could happen, and I would just round. So. Okay, sound good? All right, now let's look at our transform section. Okay, so our transform section. So bear with me. I'm going to try and be somewhat artistic here. All right, so let's remember we have an N of 9, and we have an area of steel of 3 square inches. So here's how this is going to work. So here's my beam. All right, and we have rebar here, here, and here, and this is AS, okay? And we know that this dimension here is what? D is, what was D? 17? 17 inches? And we know that this dimension is B is 12 inches. Sound good? So, first off, in order to do a transform section analysis, you have to determine where the neutral axis is. Okay, so I'm going to have this, neutral axis out here, and I really don't know where that is. Oh. There we go. Okay, now, we'll get to that here in a second. Now, in a transform section, and once the section is cracked, remember everything that's in tension, every concrete element that's in tension is assumed ineffective. So the only thing that we've got going on is we have some concrete above the section, okay? Now, it's still 12 inches wide. How deep is it? I have no idea. We're going to figure that out. So for now, we're going to call that depth X. Because I have no idea how deep it is. We'll figure it out. Now, before you draw anything, just bear with me. Now, below the neutral axis, the only thing I have is this steel. But that's a problem because this is concrete and this is steel. They're beams of two materials. So what I'm going to do is this. I'm going to transform that concrete into a lump of steel at the same location. So this is at the same location right here. So if you want, you can say that's at the same location right there, the same depth. Now, if the area of this is 3, the area of this effective lump of concrete is NAS. So what is NAS? That's going to be 27. Is that a fair point? Okay. Now let me move this out a bit. Now remind me again, I can do better than that. How far is it from here to here? What is this depth right there? 17 inches. That's D. That's 17 inches. So if that is 17 inches, help me out. What is that depth right there? What? No. I'm talking about from here to here. 17 minus x. We don't know what x is, right? Okay? But we know, so this is 17, and that's x. So how far is this? 17 minus x. So this is 17 minus x. Would you agree with that? Now, how do we determine where the neutral axis is? We sum moments, okay? Specifically, we sum moments about the neutral axis? Okay. So let's sum moments about the neutral axis. Now what I mean some moments, I'm talking about the areas. I'm talking about the cross section. Okay? So an easy way of looking at this is I want to look at everything above the neutral axis and I want to look at everything below the neutral axis. So let's talk about above the neutral axis. What do you see above the neutral axis? I don't know about you, but I see a big box right here. Right? What is the area of that box? 12x. Okay? Now, let's talk about moment arms. How far is it from the neutral axis to the centroid of that box? Half x, right? X over 2. So, how about this? Moments, we have 12x times x over 2. Those are all the moments above the neutral axis. Those have to equal the moments below the neutral axis. Now, what is going on below the neutral axis? What is the area below the neutral axis? 27, right? Now, what is the moment arm? How far is it from the neutral axis to the centroid of that lump of concrete? 17 minus x. So this is 27, 17 minus x. Is everybody okay with that?
What exactly is like the cross-sectional because I get like the cross-section of the rebar or like the transform section. What exactly does that represent?
What do you mean?
Like why we cut it in half and then the other part of the block is elongated. What does that represent?
So what the beam really looks like is we have this concrete up top and then we have a bunch of rebar. We're assuming that all this concrete in tension is useless. But we can't analyze a beam that's made of two materials. So I'm turning this into just like a lump of concrete so that I can analyze it using sigma equals my over I. Because those, remember, those equations only are applicable when you have a beam of one material. This is a beam of two materials, so we have to transform it. Is everybody else? This is fine. I mean, you've got this is good stuff. So, everybody okay with this? Now, at this point, this is algebra, okay, in order to determine x. So, over here on the left, we have 12x times x over 2, so that's 6x squared. And so we have 27 times 17, so that comes out to 459 minus 27x, right? Remember, got to multiply that out, distribute that multiplication. So we have 6x squared and we have that. You can do that, right? Nobody's saying anything. You can do that, right? The Casio FX115 ES Plus can, right? That's an engineer's answer right there. Can you do that? The Casio can. So help me out. This is a quadratic equation, so that means there are two solutions for x. What are the two values? Tell me what you're getting. You should get two roots, an x1 and an x2. So 6.78, we'll say 1. And what's the other one? Negative 11.281. Do I have seconds on that? Okay. What can I do? I have two roots. Which one doesn't make any sense? The negative one. The neutral axis is not a foot above the beam, right? It doesn't make any sense. So, so what is the neutral axis? It is 6.781. Sound good? Now, that neutral axis, keep in mind, that is where the centroid is. The centroid of the cracked section. So because of that, if I want to compute the moment of inertia, I can do so, but I can do it in a little bit of a shorter fashion. So Like I'm going to draw a table very similar to what we've seen before, but it's going to be a lot shorter, okay? We're going to have a shape. And so we're only going to have two shapes that we have to consider. I'm going to call this the concrete and the steel. Now remember, it's not steel, it's an equivalent lump of concrete, but I just want to use a naming convention that we're all pretty familiar with. So because we've already determined where the centroid is, we don't need the A, the Y, the AY, the all that. All we need is a column for the I naughts, a column for the A's, and a column for the D's. It's actually pretty easy. Okay, so we'll set it up something like this. Now, I'm going to take the concrete and just do it all, and then the steel and do it all. So we're going to take each row one at a time. Now, what's our X value? What was it, 6.78? Okay, all right. So let's start off with the moment of inertia. What is the moment of inertia of that concrete block above the neutral axis? It's the width times the height cubed over 12, right? So that is B x cubed over 12. Would that be a fair statement? Pretty straightforward. So that's 12 times 6.78 cubed over 12. Is that a fair statement? And so what does that come out to be? Let's see. I'm getting 311.8, something like that. Is it 311? Is that about right? Well, I'm putting 8, so you just deal with it. I'm kidding. But I am going to leave 8. All right. What's the area? What's the area of that box? So what's the formula? It's just B times X, right? So BX. So yeah, so 81, yeah. So 81 point, so we've got 12, 6.78. And so something like 81.37. Something about like that. Okay. And then the depth. What's the depth? Now here's the thing. What is that D value? It is the distance from the centroid of the whole thing to the centroid, to the centroid of that block. So how far is it from the neutral axis of the whole thing to the centroid of that block? What's that? Well, no. It's x over 2, right? Yeah, so it's just remember, we know where the centroid of the whole thing is, so how do you get to that block? To the centroid of that block? Just halfway up, right? So it's just x over 2. And so that is 3.39. And so now we can do I plus AD squared, and what does that come out to be? Like 12.7.54, something like that. I did this in Excel, so I think I'm probably tracking decimals a little bit differently. So something about like this, right? Now, that's the concrete. What about the steel? Now I'm going to skip one for a little bit. What's the area? It's 27. All right, what's the D value? How far is it from the neutral axis of the whole thing to the center of the steel? 17 minus X. So it's basically, yeah, so we can say D minus X, 17 minus 6.78, which is 10.22? 10.22. Now, what about the moment of inertia? Okay, here's the thing. Remember, we transform that concrete or that steel into an equivalent lump of concrete. Well, in order to compute a moment of inertia, you need a width and a height. But that's not really what's going on here. I draw this as like a little rectangle, but it's really just a lumped value at a particular point. It doesn't have a width. It doesn't have a height. It's just a 27 right there. So what is the moment of inertia of that lumped value right there? It doesn't have one. It's 0. Okay? There is no dimension to it. There is no width. There is no height. It's just there. So, does that make sense? And even if you tried to come up with some dimension that makes sense, you'd be stretching, and then even if you did, though, the I value would be so tiny anyways, it'd be negligible. So what is I plus AD squared? It's just AD squared. And so what is that? Say it again. 2820.1. Do I have a second on that? And so sum that up, and what do you get? We'll say to the nearest whole number, just to keep it simple. 4068. Do I have a second on that?
I got 46 to say.
Do you hear him?
Yeah.
Okay. There are far more pressing issues than this. All right. So let's sort of put some scale on this so everybody is aware. Let's recall something. I just want to make sure everybody's clear on what's going on and what these values represent. Remind me, what was the gross moment of inertia of this section? 8,000. I propose that this value is the cracked moment of inertia. Does it make sense that it's smaller? Yeah, it makes sense that it's smaller. You crack the beam. It's not going to suddenly get stronger, right? Remember what I is. It's a measure of the stiffness of a cross-section. The larger the I value, the more stiff it is. So once it's cracked, it makes sense that I suddenly drops down, right? Now, to go back to what I was saying earlier about when you look at deflections, some of the beam is cracked and some isn't when you look at deflections. So the question is, where does it fall in between? And you use a weighted average formula, but that's discussion for later. So far so good? All right, any questions? Yes?
Why were we able to use these areas?
What's that?
Why were we able to use these areas?
That's a great question. And the answer is, how is that any different than when you compute a centroid? What do you do when you compute a centroid? Like sum of AY over sum of A. You're taking an area times a moment arm. An area times a moment arm. And dividing it by the sum of the areas. This is really no different, only instead, in order to do that, we have to get to a situation where we can solve for x, and the only way you get that is you have a quadratic equation that you end up solving for. I mean, basically, how do you compute a centroid? You're taking a first moment of area, an area times a distance. What do you think? No. It'll always, because of the nature of the problem, it'll always figure itself out. Now, let me say this. There are instances, let's say if you have a T-beam, you might have to recalculate it to where your axis is, let's say below where the flange is or above where the flange is or whatnot. But no, you'll never have a neutral axis above the beam. You could also have a scenario where mathematically you get an answer like x equals 30, but the beam's only 20 inches deep, so it's way below it, and that wouldn't work either. So, so yeah. Any other questions? This is good stuff. Now, we're not quite finished with this problem because we still have to compute bending stresses. Okay? This is a simple calc. You just got to make sure you're clear on what's going on. Okay? Now remember, we have a bending moment of, what was the bending moment on this problem? How much did we put on it? 70 foot kips. Okay, now remember, that's 840 inch kips or 840,000 inch pounds. Again, if you're not comfortable with that, I have absolutely no problem with you all putting it on your formula sheet on your exam, but you're going to be doing some unit conversions, so just make sure you're comfortable with it. Now we have a cracked moment of inertia of 4067 inches to the fourth, and what was our x value? It was 6.78 inches, something like that. Okay. All right. So what we're going to do is we're going to compute a stress in the concrete and a stress in the steel. Let's compute the stress in the concrete first. Okay, now remember, all we're doing, we're basically, this is just my over I. That's all this is. Okay, so let's take care of the stress in the concrete first. Okay, so first off, we have M. Now, our moment of inertia is going to be the cracked moment of inertia. Now, what about Y? Remember, what we need to do is we need to figure out how far is it from the centroid to the very, very, very tippy top of the concrete. And what is that value? Now, think about it. How far is it from the centroid to the very, very, very tippy top? What's that? Y'all are guessing. No. We're talking about the centroid of the cracked section. Remember, the section's cracked. So we're not looking at just the rectangular beam. We're talking about that cracked section. Where is the centroid? Now, hold on. Here's this cracked section right here, right? Where is the centroid? It's right here. So how far is it from the centroid to the very, very tippy top? It's X, right? It's 6.78. How far is it from the centroid to where the steel is? 17 minus X, right? Make sense? Okay, all right. Okay, so this is X. All right, is that clear? I mean, I want to make sure everybody's clear on that because I'm getting some looks like we are. What? No, remember, the neutral axis is where, first off, remember, sigma equals my over I. Y is always measured from the neutral axis. The neutral axis is where there is no bending stress. Remember, this is the cracked section. Everything above the neutral axis is experiencing compression. Everything below is experiencing tension. That's why we neglect all of this concrete. This is where there is zero bending stress. So that's why we're saying that's the centroid of the cracked shape. Okay? So how far is it from the centroid to the very, very tippy top, the worst case compression? It's X, right? Does that make sense? Everybody else okay with that? I mean, I want to make sure this is clear, so. Exactly. And keep in mind, we're talking about 70-foot kips of moment. If we were talking about 10-foot kips of moment, then when everybody was saying 10, That would be correct, because at 10-foot kips of moment, the beam hasn't cracked yet. Everybody okay with that? Everybody good? Okay. All right. I knew you had a question.
I'm still hung up on the area times the lever arm, right where your cursor is right there. I've been looking at it. I thought there was an easy way to understand it. I was just missing it. But it's 12x, which is the area, times the lever arm.
Yes. Yes.
And then it's the area, 27.
Yes.
17 minus x. Why is that not divided by 2?
How far is it from here? Hold on. How far is it from the neutral axis to the center? How far is it from the neutral axis to the center?
How about 17 minus x?
No. Remember, the 17 goes to the center of the steel. So this is 17 minus x. That's that distance.
That's technically the steel portion doesn't really have dimensions because there's no dimension.
It's just a singular lumped value right there. All right, everybody okay with this? No. Okay, good. What about everybody else? Yes. Remember, this is after the cracking moment. Once the cracking moment has been exceeded, it's cracked. So the concrete in tension is not doing any good. I mean, think about it. Imagine you have a beam and then you got a crack right there. That part right there isn't experiencing any stress. It's not doing anything. That's a way of looking at it, yes.
So it only cracks the rebar.
No, it cracks up until the neutral axis, but the rebar takes over to handle the tension. Without the rebar, once you exceed the cracking moment, it's over. Think of in materials lab, once you test those beams, once it cracks, it's gone, you know. But if you put rebar in there, it'd be able to withstand moments well beyond the cracking moment. Everybody okay with this? Okay. All right. So let me finish this real quick. All right, so we have, so we have a moment, 840,000 inch-pounds, 6.78 inches, and then 4068 inches to the fourth. Here, I'm going to rewrite that. And so what does that come out to be? 14,000? I got 1,400. 1,400 PSI. Now, just to be clear, are we within what this concrete can handle? What's the maximum compressive strength of the concrete? 3,000 PSI. So we're well within what the concrete can handle. Like, just because it's cracked doesn't mean the beam is done. The beam can withstand loads well beyond. Okay? Now, we're not done. We got one more calc to do. We got to determine the stress in the steel. And this is, well, you tell me, is this stress in compression or tension? Remember, beam's being bent like this. So the bottom is being yanked on, the top's being...
So right now we're only calculating
That's the concrete over the neutral axis, and that's the worst case stress in compression. Now, we still got to do the steel, okay? So what's our bending stress formula going to be? It's going to be, we have a bending moment, we have a cracked moment of inertia, and what's the distance? It's 17 minus x, right? Because we're talking about the stress in the steel. Okay? Now, This is where I think you're not going to like me very much, but you got to remember this from deformables, okay? Remember, mechanics of deformable bodies, these fundamental equations only work when you have a beam of one material. We have a beam of two materials, okay? We're computing the stress in the steel. What's going to happen is if we just compute this using this formula, the answer is going to generate a stress that's far less than what we're actually seeing. The reason why is because we have to reintroduce N, our modular ratio. Because the material is much stronger, the stresses are going to be higher. So this is going to be what was N? 9? 9. Let's just even number.
Be 19,000.
19,000 even?
Yeah, I mean, it's 18,997.
We'll say 18,997. Now, is that anywhere near the maximum yield stress for regular rebar? What's the yield stress what's the yield stress for regular rebar? No. 29,000 is the E value. Remember if we had, like, say, grade 60? 60,000 PSI, is that anywhere near what steel can handle? No, that's only 19,000 PSI, but the yield stress of steel is something like 60, so it can handle well beyond this. So I want you to understand that the actual maximum capacity of the beam is well beyond cracking, Okay, the cracking moment is just a small little bit of its capacity. It can handle well beyond. Is everybody okay with this? Okay. Next time, we're going to talk about maximum capacity. I am going to introduce a little bit of the C word, a little bit of calculus, a little bit, but we'll get there. That's all I got. We'll see you.